Welcome to this lecture class of the course Computational Hydraulics. We are in module 4 surface water hydraulics, and this is unit number 2 gradually varied flow implicit approach. In our previous lecture class we have discussed about gradually varied flow using explicit approach. Now, learning objective of this particular lecture class, at the end of this lecture class students will be able to solve gradually varied flow problem for open channels using implicit method. Now, this gradually varied flow we are considering for single channels. Problem definition to solution, this is our general framework. In our previous lecture class we have got solution which is y as a function of x from the governing equation dy by dx equals to S naught minus Sf 1 minus Fr square, and this is initial value problem. So, from our definition we do not need boundary condition in this case or initial condition, one sided condition is there. So, this is our first order ODE differential equation. Now, to solve this with the structure of the explicit method, we can directly transfer all the known quantities on the right hand side and only unknown quantity on the left hand side. So, directly we can get the solution using explicit approach. However, if we utilize the implicit approach for the solution of GVF or gradually varied flow, we need to solve it either using this linear equations or nonlinear equations as per our requirement. But in this case the equation this term SF, which is a function of y, and Fr which is again a function of y, these are nonlinear in nature, obviously we will be getting nonlinear equations. So, we need the solution approach for those governing equations or discretized governing equations. Now, let us consider our basic problem statement. So, problem definition is governing equation for gradually varied flow in prismatic channel can be written as dy by dx equals to psi xy with psi xy equals to S naught minus Sf 1 minus Fr square, and in this case n is Manning's roughness, q is a discharge. Obviously for a channel maybe it is a specified discharge. R to the power 4 by 3, R is hydraulic radius, A is area, T is top width, Q is again discharge, G is in this case this is acceleration due to gravity, A is area, and we have this initial condition on one side. So, these are the expressions that we can directly utilize for our problem. Now, what is given and what is required for our problem solution? Given, let us say that we have a given channel cross section type is rectangular, then y naught, which is the initial value at x equals to 0. This is 0.8 meters. Then B, which is bottom width of rectangular channel, this is 15 meters, G is 9.8 meter per second square. Then S naught is 0008, N is 0.015, Lx length of the domain or length of the problem which we need to consider, Lx is 200 meters, and Q is 20 meter cube per second. Now, in this case required is that we need to identify the type of GBA profile from the problem and plot of the GBA profile. So, this is for rectangular cross section. In our previous lecture class, we have seen that we can have two different slopes for a trapezoidal cross section. So, this is a general slope feature. If this m equals to 0, m1 and m2, then we can get rectangular cross section in that case. So, in this case we have top width equals to bottom width or channel width and y. So, this area is b into y, p is b plus 2y considering depth on both sides. So, this is the weighted perimeter for the channel. Now, r, which is hydraulic radius, is a by p. This is nothing but by b plus 2y. Now, in this case r is again a function of y. For given b, your flow depth can vary. So, in this case r is function of y. So, in this case we can find out the critical depth, to define the GVF or gradually varied flow profile. We need the level for NDL, which is normal depth line, and critical depth line. Critical depth line is corresponding to this FR equals to 1, and normal depth line we can find out from Manning's equation. So, for the first case, if FR equals to 1, then q square T by GA cube, this is 1, and from there we can get this QC, which is q square G B cube 1 to the power 1/3. Now, for rectangular channels, if we need this normal depth, we can use Manning's equation. In this case, please remember that we are using S naught, and rectangular channel case, if we represent yn as normal depth, so this is area and this is perimeter. Now, for a given discharge, slope, and n value, we can find out unique value of yn. So, that is the normal depth in this case. So, we can write this as general function gyn, which is nothing but this quantity minus the quantity on the left hand side, and we can equate it with 0. Now, this is one nonlinear equation. Now, if you want to solve this problem, we need to use our Newton-Raphson technique, and from our Newton-Raphson technique we can get the solution by iterative approach. This y and p is the iteration count in this case. So, y n p minus 1, this is from coming from previous iteration. So, we can start with y n p 0, and maybe we can start from y c value, because we have already got the y c. If we have this y c value, then either or CDL location, then either this NDL will be on the upper side or lower side. So, it is safe if we start from this YC, which is the guess value for the normal depth iteration process. Now, in this case we need to find out what is this G prime. G prime is nothing but this is dG divided by dyn. Now, this quantity we need on this denominator, and this should be calculated based on the previous iteration value, and this is our original function value which is g function, capital G function. Now, from this iteration process we can get this yn. Now, if we see this implicit Runge-Kutta methods, in our previous lecture class we have seen that explicit method, this counter which is I, in case of explicit method this was up to I minus 1. So, this was up to I minus 1. Now, in this case we are going up to I, that means whatever value of this increment k I is there on the left hand side, we are also incorporating that k I value during calculation of psi. So, in a way this increment equation is implicit in nature, and we have different weights Wj, Kj. J is running from 1 to m, m is the number of weights or number of points or number of increments that are required for calculation of this weight. Now, in this case we have Cix or increment for x direction and increment for our y. So, Cx, this I is increment corresponding to ith increment parameter, and this Cij y, this is general increment parameter for yn. Now, in this case if we consider this Bouchard tableau, this can be expressed in general terms with this format. So, we have let us say m terms or m increments. Now, for each increment we need increment in case of y x. So, this is corresponding to increment for x or xn, and on the right hand side this is for x, on this side we have increment for y, and the bottom portion we have different weights. So, if we consider the portion which is for y, that is one matrix and size is m by m matrix. So, each row is representing the coefficient of the corresponding increments that are required for the calculation of flow depth y, and the first term in this row, this is corresponding to increment for x. So, this is corresponding to x, and these values are corresponding to different coefficients that are required for the calculation of coefficients here, and these weights are related to the final calculation. Now, if we express it in terms of reduced matrix form, we can write this as column vector. First one is one column vector, and this is a row vector. This is a row vector. So, we can in general we can express this as column vector, and we can take this transpose here, and capital C y, this is the full matrix here. So, this is the general representation of using Boucher tableau. Now, using this tableau we can represent our Runge-Kutta methods, and if we start from our well known basic approach, which is backward Euler. In backward Euler, let us say that this is C x 1 and this is C y 1 1, that means only one term is there, and on the bottom we have W 1 which is again equal to 1. So, what will be the structure of our increment? Increment will be k 1 equals to del x psi, in this case x n plus this is 1. So, directly we can add that del x comma, we should have y n, again the coefficient is 1. So, in this case we can write it as k 1 and this is our case, and which is the coefficient of this k 1, and finally we can add this y n equals to y n plus W 1 which is again k 1 in this case, because W 1 equals to 1. So, from this process we have identified the backward Euler method. So, in general terms, if we write this is x n plus 1 y n plus 1, this is y n plus 1, but y n plus 1 is unknown thing. So, we cannot solve it using our usual explicit approach. We need to solve this equation here. Now, in this case again we can write a general function because y n plus 1 is unknown. So, I can transfer this y n plus 1 and other terms on the left hand side. So, y n plus 1 which is coming from here, this is my second term, and the third term which is a known quantity. So, this part is unknown and this is a known quantity, known or unknown and known quantity in this case. So, again this is nonlinear equation and we can solve it to get this y n plus 1. Now, in this process if we write this general equation which is y n plus 1 p y n plus 1 p minus 1, which is again the value which is coming from previous iteration, and these are the function value and derivative of the function value. So, initial was y n plus 1 minus del x into psi x n plus 1 comma y n plus 1. Obviously, if we differentiate this one with respect to y n plus 1, which is the unknown quantity here, this is y n plus 1 and minus y n. So, initially this quantity is not significant here, because if you differentiate it with respect to y n plus 1, this will be 0, this is 1, and on the from the second term we are getting this big expression for rectangular channels. Now, if we write a code for this one, we can get the solution out of this. So, in this case, if we start this Scilab, so we have GVF implicit. In GVF implicit, backward Euler. Now, given data from our problem statement, Q is 20 meter cube per second, S naught is 0.0008, N is 0.015, bed width for rectangular channel, that is 15 meters, G is 9.81, Lx is 200, Y is 0.8 meters. Now, with this let us say that M node or nodes in the M or Lx direction, that is 201, and these values are global Q, S naught, N, B and G. In this case, first step is critical depth calculation, YC as Q squared G B squared and whole to the power 1/3, we can get the YC value. Then normal depth calculation, G val and G prime val. So, G and G prime, these two values are required. So, using Newton-Raphson here, we can get the solution and we can get this Yn. So, after getting this Yn and Yc, we can comment on the flow condition. So, obviously, if your Yn is greater than Yc, we have mild slope condition, and if Yn is less than Yc, we have steep slope condition. Now, first case we have dy by dx equals to psi xy, our general governing equation in this case. So, this is B y, b plus 2y, r is ay divided by py. Now, we can calculate this dy by dx. Next step is f val, because we need that function val. Y is actually y n plus 1, this is delta x into psi x comma y, and at this step we have this minus yp, yp is previous time level value. Now, we need to calculate this term by term fp val or derivative of f with respect to y y n plus 1. Now, if we check the first term here, so this is 1 minus q square divided by b square g y cube n plus 1. So, same thing I have written here to the power minus 1 to the power minus 1. Then second term 2 n square q square b square y cube, which is the second term here. Third term is b y n plus 1 b plus this 2 y n plus 1. So, same thing, if I write here, this is the thing. Now, like that I have written all the terms in this f prime calculation 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 terms here. Now, after getting these terms we can simply this is term 1 into term 2 into term 3 plus term 4 term 5 times 6. So, we can get this fp val or f prime value from the this derivative calculation. Now, we need to use this one in our backward Euler method. So, first of all we need to have this grid which is xc, xc is running from 0 to Lx. We have all total m node number of nodes, which is 201 in our case. In this case Lx is 200 meters, and delta x is Lx or delta x is Lx divided by m node minus 1. So, this is individual del x we can calculate. Now, in this case yv is our variable, we need this y value. At the starting we have yv1 equals to y naught, yv1 which is specified at the first node, this is y naught. Now, we can start our calculation for I equals to 1 to m naught minus 1. So, epsilon max, this is the iteration parameter 1 into 10 to the power minus 6, AE error, this is 1 or absolute error in this case. Now, in this case we are starting with the guess value y v I plus 1 equals to y v I. Now, we should iterate if absolute error is greater than epsilon max. So, what is this absolute error? Absolute error is absolute value of AE error. AE error is f that means function value at y n plus 1 for previous iteration divided by f prime y n plus 1, that is also calculated based on the previous iteration. Now, this is minus and this is y n equals to y n plus 1. So, from this one we can get the solution. So, this is our in this case in this case we have this y n plus 1 which is coming from iteration p, and this is y n plus 1 which is coming from iteration p minus 1 and minus f by f prime, and this was y n plus 1 not y n. So, we can use this for calculation of Newton-Raphson. Now, this is minus error, this is x c y. Now, if we run it, similar to our explicit method, we are getting M2 curve. In this case, this is NDL or normal depth line, this is CDL or critical depth line. From our calculation point of view, this yn is 0.8478 and yc is 0.5658. Now, if we try to utilize the higher level methods or higher order methods in this case, then if you have implicit Runge-Kutta, in this case please remember that we have this y k I and I is there, that is why it is implicit. Now, what we can do, we can split it into explicit part plus some increment, the C I y k I, this is the increment part. So, we can write this quantity, this is again explicit in nature. So, this is explicit, only implicit is this quantity, this is C y I I. Now, in this case we have this delta x which is only C I del x, and delta y which is our j equals to 1 to I minus 1 C I j k j, this is explicit quantity. Now, in this case we have this psi x n plus delta x y n delta y C I y I k. So, this is the increment part. So, we can expand it with Taylor series, and this is a first order expansion. So, on the right hand side we have x n plus delta x, y n plus delta y, and C y I this is x n delta x y n delta y, and this quantity is multiplied there, and we are differentiating with respect to y here. So, in this case uh, if we combine the terms, so this is k I delta x into psi, which is our known quantity, and this k I is unknown. Now, if I transfer this thing on the left hand side, so I can write this as one minus C I and y, this is delta x psi plus prime into k I in this case, and this is delta x into psi x n delta x y n plus delta y. So, I can transfer this on the right hand side, this is the inverse term del x. Now, from this case we have this psi prime, the psi prime value we can calculate, and we can directly get the k I value here. So, k I value we can get in terms of known values, because x n del x, y n del y and psi prime, these quantities are known, and for a given Runge-Kutta method C I y, this quantity is, or this parameter is known, and del x is fixed for a particular problem. Now, in this case, if we utilize it for second order RK method, or RK2, then considering the Boucher tableau, we have half half, that means coefficient of x is half, coefficient of y is half. So, this is nothing but k1 equals to del x, and we have psi x n plus half del x comma y n plus half k 1, and final thing is y n plus 1 equals to y n plus k 1. So, if we utilize this, this is second order method. Now, what should be our approach? We can expand this, and expansion is in terms of our known quantities. Now, in this case we can expand this part using Taylor series as psi, this is x n plus half del x, this quantity is y n, which is known, plus we can write psi prime, and we can multiply our half into k 1 in this case. If we multiply again del x outside and equate it with k 1, we can get the this particular format. So, on the right hand side we have all known quantities, psi, psi prime, these are known quantities on the right hand side. So, we can get this k 1 value. Now, if we see the code for this one, this is RK2 implicit. First portion is same. In this case we have RK2 method. We need grid data in this case also, xc, delta x, yv, this is y v 1 equals to y naught, and then we are calculating this k 1. Now, k 1 in this case this is coming from this known quantity, this is 1 minus half delta x p psi or psi derivative. These are known quantities, this is psi derivative, this is psi value directly, and we are considering inverse of that value, and we are adding this k 1 with our previous time value to get the final plot. Now, in this case we have RK2 method. Now, let us try to plot this thing on top of our previous solution. So, this is with a red color. Now, if I compile this, so it is coming here. Now, it is interesting to see that red line, which is RK2 method, is somewhat on the upper side, that is it is giving higher value compared to the blue line, which is our backward Euler method. Now, if we further increase the order of RK, second order RK approach, we have this thing. Now, considering the fourth order RK method, which considers these many points, that means we have 2 entries here and 2 by 2 matrix for Cy, this is for Cx, this is for Cy, and this is for W1 and W2. Now, with this if I write this RK4, this is RK4 in this case. So, RK4 is half half because this is W1, this is W2, and we have these terms, this K1 is equal to del x into C1, which is coming from here, the first quantity, this C2 is coming here, then C11, this is the first one, C12, then this quantity is C21, and last one, this is C22. Now, with this if we try our method or approach, we can get the solution. This is fourth order RK. Now, in this case we have K1 and K2. Now, for K1 and K2 for both the cases we can expand it. Now, expansion is in terms of both the terms, only yn is known, K1 and K2 both are unknown. So, this is our increment. So, psi prime, psi, these are known quantities now. Now, this is coming from Taylor series. Now, next step is a calculation of K1 K2. Now, K1 K2 can be calculated by solving this system where we have 2 by 2 matrix, which is the coefficient matrix. On right hand side also we have known quantity. Now, we can solve it using our standard approach and utilize it for the solution of fourth order RK. Now, if I open this fourth order RK, the first portion is same. Now, in this case this is RK4 method. I have created this AK, which is coefficient A or coefficient matrix for k. This is 2 by 2 zeros. Now, we have this Cx1, Cx2, Cy1, C11, Cy11, Cy12, Cy21, Cy22 and y1 equals to y naught. These values are available. Now, within this calculation process, starting from y equals to 1 to m node minus 1, we can create that AK or coefficient matrix, then calculate this k and Rk, which is on the right hand side. So, AK is coefficient matrix. So, in this case we can solve it using internal function. This Kv, which is k value we are directly getting from this backslash, this Rk. Now, from this one we have k1 and k2. So, half of k1 and half of k2, if we add with the previous section value, then we can get y I plus 1 in this case. Similarly, this approach is our RK4 approach. Now, I can plot this one. This is again a red one or magenta. I can change the color in this case, and if I run it again, it is coinciding with our second order, or it is near about value of our second order method. If we zoom it, obviously we will get some difference for this one. Now, in this case we have seen that using backward Euler, second order Rk and Rk4, we can solve our GBF profile equation, that is the first order initial value problem with implicit equations, and we have discussed this backward Euler approach, Rk2 approach, Rk4 approach. Now, you can utilize these codes for running and for running the GBF or running and creating the GBF profiles, and you can change different values and get different kind of GBF profiles out of this. Thank you.